So, when we were doing that perturbation theory and we were finding different susceptibilities, while finding third order susceptibility, if we take the degeneracy factor, then it should be 6. But,
Uh-huh.
in the book, when I go through the equations, they have mentioned that permutations are 6. But when we carry out this prescription, we found that only 3 contributions occur. And then they take the degeneracy factor as 3. I couldn't understand the reason behind that.
So depends on the process, right? Like if you have like 3 different frequencies in your input, omega 1, 2, 3, then there are 6 different permutations, right?
Yes, sir. But they have taken it as 3 later.
Yeah, I don't know what exactly you're talking about. Like if you want to calculate like this, for example, right? So some process like you have 3 different frequencies giving rise to, let's say, that sum, right? So now, so you have 6 different permutations for this. So when you write the expression, um, or when you write the nonlinear polarization corresponding to the frequency omega 1 plus 2 plus 3, then you'll have a factor of 6 here. If you take just this term, right? Basically, what we are saying is, okay, we have this term, then we have the term where we just permute these, and there are 6 of them, right? So I can write omega 1, 2, 3 in 6 different ways, in 6 different ways of ordering, right? So in the level diagram, it's like saying, okay, I can show the picture like this, or I can show like omega 3 first, omega 2, or whatever combination, right? It's the same process. So sort of, yeah, it's 6 different ways of the same process occurring. So if omega 1, 2, 3 are different, then you get 6 here. But in some cases, for example, when we looked at third harmonic generation, when all 3 of these were equal, right, then this factor is only 1 because there is only one permutation, right? So if 2 of these are equal, for example, then 3. So depends on what particular process you're looking at and what are the number of.
Okay, sir. Then after this, when we found the displacement, when we said that the displacement in an atom due to electric field is equivalent to the radius, then linear and non-linear effects become similar.
Yeah, so that is sort of a heuristic estimation, right? So we are saying, okay, let's say the electron cloud has some size, right? So, and when you apply the external field, this gets distorted, and if the electron gets pushed or displaced by something of the order of the atomic radius, then we are seeing that the cloud is getting really distorted, and the nonlinear and linear contributions become comparable.
Uh, do we have anything that proves this, or do we assume it?
No, it's just as I said, it's like a heuristic estimation, right? So you have some very small term which grows as, right? So the nonlinear term is initially very small, but it grows nonlinearly with x, right? And basically, we want to estimate at what point does the nonlinear term become comparable to the linear term, and basically the only length scale here is just the atomic size, right? That's sort of the only length scale in the problem. So we are saying, okay, when the displacement becomes of that order, yeah. So it's an approximation, right? So
Okay, sir.
it's just of the order. We don't know if it's twice d or d by 3, because we haven't taken the exact atomic potential, right? It's just a crude approximation. But as we saw, like the values that we estimate from that turns out to be quite close to the actual values.
Okay, sir. Sir, I have one more doubt. Uh,
Yeah,
the last topic where we considered spatial symmetries. Um, so in third order susceptibility again, we found that the order 1122 has non-zero values.
yeah.
So this means then when I have two fields in two direction and one field in one direction, then final field is in one direction and polarization is in one direction. But when I have 1112, then we say that its value is 0 or 1112.
Yeah.
So then we have two fields in one direction and one in two direction. So overall field can be in direction one. So why it is always 0 for 1112? I couldn't find the reason behind it. Physics.
So think about it. So think about some other configurations that you can do. So right. Um, um, so in an isotropic medium, basically the nonlinear polarization which is induced has to be parallel to my direction of the total electric field that I apply. Okay, so let's say I apply a bunch of fields, whatever is the resultant of them, the induced polarization has to be parallel to that, because there is no direction in the isotropic medium, right? So, right. So this uh, basically constrains which elements can be present and which cannot, right? So you can think of combinations like, let's say you apply some one particular. So when you have these IJKL, right, it doesn't mean that you need to apply three different fields. Like for example, we saw your third harmonic condition. The input field is only one frequency. All the three terms of the electric field come from the same field, right? So there we had something like the P is proportional to the Kite-Helmer times E cubed. Right, so all the E's are coming from the same field. I just have one input field. Right, so you can think of combinations such that you apply some field in some direction and you want to see polarization induced in some particular direction. Right, I mean it's straightforward. You automatically see that because of this, all the elements where three of them are the same have to go to zero.
When three of them are same, like you gave an example of 1 2 2. So we can say all three are in two direction. So resultant can't be in one direction. It is 0. And if I apply the Lyman's approximation, then I can say that if 1 2 2 is 0, then
Yeah,
1 2 1 2 2 can also be 0, because we can exchange the terms. But what
yeah.
is physics behind it? I'm not able to understand this. That why when I apply two fields in direction 2 and one in one, then why can't it give me a field in two direction, electric field or polarization?
So that's not the only. So let's say you apply whatever two fields in two direction, one field in one direction, right? You have to calculate what is the total field that will be generated, right? So not only that element will contribute, but other elements might also contribute.
So what elements? I'm not.
So then you have to see for different combinations. If you have to satisfy this, then you'll see that.
Then why do we say that 21 always exists and it is non-zero?
Yeah, because I mean, again, from this constraint, turns out that that is non-zero, right? It's not, or that is not constrained to be zero. Like the ones with 3 of them equal are constrained to be zero already from here. So yeah, but the ones with 2 of them equal are not constrained to be zero. They might happen to be zero in some strained material, maybe, right? But um, in general, they're not constrained to be zero, and turns out in most materials they're not zero. And then we also derive a relation between the when all 4 are equal, right? Like at least in, for example, in the Kleinman symmetry case, there is a relation between the element where I is equal to j is equal to k equal to l, and then when both of them are equal, right? One is 3 times the other or something, right?
So how do we derive this if we don't remember them? How do we know the logic?
So, I mean, if you go through, so the first chapter of Boyd has a couple of sections on symmetries, right?
Can
So
I
there
check?
are other kinds of constraints. Like for example, um, the fields have to be real, the polarization induced have to be real, uh, right? Then the field energy that uh, so when you apply an electric field and you induce a polarization, there is some stored energy in the material, right? And
Okay.
then basically how that energy is, so that should be basically path independent. So for example, if I first apply E1, then E2, then E3, or if I apply first E2, E1, E3, should not matter. Final field energy should just depend on the final configuration of the fields. So there are a lot of so realistic considerations like that, which gives rise to all the symmetries, right? I didn't go through all of them in very detail because, yeah, it could take like 3-4 lectures on their own to go through symmetries. But I just went through what is sort of important for most practical applications are the isotropic and the cubic case. So,
Okay, sir.
but yeah, if
Thank
you're
you.
interested to go deeper into this, you can, as I said, go through Boyd. So that has a
Sir,
little bit
actually,
more.
I went through the book, but I was not very much clear. I couldn't find very much of isotropic material susceptibility in that. This isotropic thing was not discussed in detail in that book. I went through so many sources, but all the
Yeah,
sources mentioned these values.
maybe you have to go to secondary sources, right?
Yes,
To,
they are
but
mentioning the values.
in isotropic medium, the main sort of consideration is this, right? So you
Okay,
can think of arbitrary fields that you apply, and then you have to make sure that the induced polarization is parallel to that, and then from a few combinations, you can see which terms have to be zero and which uh, are not zero and which are related and which are not.
okay, sir.
So just yeah, maybe think a little bit more about it. Try different combinations of fields and see. Uh,
Okay,
right. So
thank you, sir.
you could apply a field in some like XY plane in some direction. You could apply it in XZ plane in some direction. You could apply, right? So you could
Yes.
do lots of different things.
Okay, sir. Thank you so much, sir.
Okay. Any other questions before we start today's class? Okay. Um, so I think there was a question in the last class. Somebody asked that. So the response of material typically has some characteristic time constant associated with it, right? It's not instantaneous. So, for example, when we apply a field or apply some combination of fields to a medium, the polarization is induced, right? But typically, it's not instantaneous, right? So there will be some time delay between the application of fields and the polarization which is induced. Um, so in the first two classes, we sort of looked at the susceptibility as a function of frequency, right? So depending on the order of the susceptibility you have, the order of the susceptibility you'll have. So if it's chi n, then you have n different input frequency variables here, right? And that kind of description is useful for when you have monochromatic fields interacting with each other. Right, so you have, let's say, a bunch of lasers at specific wavelengths which are interacting with each other through some nonlinear medium. So this kind of, am I writing it over the reflection? Is it visible or not?
Visible.
So this frequency domain description that we wrote, right? So, as a function of frequency, that is useful for analyzing monochromatic fields, right? When you have optical fields at specific frequencies which are interacting with each other. And so this gives rise to, for example, some nonlinear polarization at frequency, at some particular frequency. But let's say if you have like optical pulses, right? So you also have pulse lasers, for example, right, where you get power as a function of time, and these pulses can be quite short. So basically, if you look at the Fourier transform or in the frequency domain, they have a bunch of frequencies present within the pulse, right? So there's some continuum band of frequencies within the pulse. So for such interactions where you have optical pulses involved, right, a time domain description is more useful, right? And so for like, you could have these pulses as short as, let's say, tens of femtoseconds to as long as, let's say, a nanosecond or something, right? So you have various different kinds of optical pulses, and basically, so we wrote, so in the frequency domain case, right? So we typically write the nonlinear polarization at some particular frequency as some degeneracy factor, and the nonlinear polarization at that frequency times the product of electric fields, right, at the contributing frequencies. So put a product here. Similarly, in the time domain, I can write. So let's look at, for example, the linear response. So the first order polarization. I could write it sort of like a convolution of my applied electric field times some response function. Okay, so this R of tau is the response function of the material, right? And so basically, to obey causality, this R of tau is 0 for tau less than 0, right? Which means the polarization at time t depends on the fields applied in the past, right? So only for tau greater than 0, so it only depends on the electric fields applied before time t, right? So that's causality. So this R of tau is some kind of response function, right? Let's say there's some characteristic delay here for the material to respond. Okay. So you can see, for example, if I apply delta function electric field, so apply impulse, then the polarization induced is basically the response function, right? So if I apply impulse electric field and see how the material responds, the polarization induced will follow this waveform. Okay, and typically, most of the time, basically what we do is, especially when we are working far off resonance, right? So if omega naught is some resonance frequency, and if we are working at frequencies which are far away from that resonance, then typically this response function looks almost instantaneous. Okay, so basically for this such a case, basically r of tau as delta of tau is a good approximation, right? So this response is just a delta, which means you can say P of t is just proportional to E of t. Okay, but if you zoom in really finely into the time scale, of course, no material is instantaneous, right? There's always some finite time delay involved in the in inducing the polarization response, right? So, for example, if you look at glass, silica, then this is of the order of like a femtosecond, 10 to the minus 15 seconds, right? So for most cases, like for example, if your pulses are 100 femtoseconds or longer, this is basically instantaneous. But some other materials, for example, like if you take some atomic vapors, which have discrete energy levels instead of bands, and then you work closer to resonance, okay, then turns out that the response time can be quite long, into even the nanoseconds, right? So then the response function becomes, you cannot ignore it, you cannot treat it as an instantaneous response. Right? Okay, so of course there is some relation between this time domain response function, right, of the material and the frequency domain value of the susceptibility, right? Both of them are describing the same thing, sort of one in time domain, one in frequency domain. So there is some relationship, and of course you can a priori guess that there has to be some kind of Fourier transform kind of relationship between the two, right? So you can easily see that if so again, so for this frequency domain case also, if we take the linear response, right? So in the frequency domain, we wrote the polarization like this. So times chi 1, right? So that's the frequency domain description for the linear polarization, right? And this is the time domain. And of course, the frequency and time domain are related. So P of omega is basically the Fourier transform of the time domain function at omega, right? So P1 of omega is basically the Fourier transform of P1 of t at frequency omega. And similarly, E of omega is the Fourier transform of E of t in general, right? Or equivalently, like I can write this as the inverse Fourier transform of E of omega, right? And similarly, E of t is the inverse Fourier transform of E of omega, right? So, for example, in this expression, if I substitute the time domain values with their frequency domain counterpart, so I replace P of t by this integral of t omega. Similarly, here you can replace E of t by 1 over 2 pi, right? So, right? So then you'll have now converted this into some frequency domain expression. So on the left hand side you have P1 of omega, on the right hand side you have P1 of omega, and you can compare the expression you get with this, right? So whatever is remaining inside the integrals, etc., has to be equal to chi, right? So you can just do that algebra, and you can see that chi1 is basically the Fourier transform of the response function. Okay. So basically, for example, if you have an instantaneous response, so if R of tau is like a delta function, then what does that mean? That my chi of omega is a constant, right? It does not depend on frequency, right? So again, this goes back to the of resonance. We saw that the susceptibilities don't depend on frequencies anymore, right? Which is equivalent to saying that the system has now an instantaneous response. Okay. But if you can see that if you don't have delta function here, if it's not an instantaneous response, then in general your susceptibility will be frequency dependent and also it will be a complex number, right? Both of those points we noted last time, right? So that's the linear case. Similarly, we can also analyze the nonlinear case. So for example, if I look at the um, third order response, right? So in the time domain in general, I can write the third order polarization as again now a response function times electric fields, but now I have three electric fields, right, coming in, and you can imagine now, so therefore I'll have a three-dimensional response function. Okay, so now my response function depends on three time coordinates. Okay. Yeah, so it's a three-dimensional function because I have three functions of electric field, so I have three different delays, right? And again, each of the integrals go from 0 to infinity. So basically, because each of these have to be in the past, right? And how is this response function related to? So again, if you compare it to the frequency domain case, so in general, let's say I have three different frequencies: omega 1, 2, 3. Right? Should have something like this. Then again, if you put in Fourier transforms relations here, you can check that the third order susceptibility at the sum of these three frequencies is basically the Fourier transform, or the three-dimensional Fourier transform of the response function, because the response function is three-dimensional. Okay. Right. So even for nonlinear polarizations, the susceptibilities are related to the response function by Fourier transform, but now they're higher dimensional Fourier transforms because these are higher dimensional functions now. Okay. But sort of the same arguments hold that we discussed for linear case. Like for example, if this is instantaneous, then this is frequency independent, etc. Okay, so most of the time the frequency domain description is fine because mostly we deal with monochromatic fields. But for example, later in the course we'll discuss the nonlinear propagation of ultra-short pulses, and there we'll use the time domain description because it's easily handled in the time domain. Right? Okay, so now we've looked at basically on the atomic scale how does the nonlinearity come about, right? And nonlinearity depends on the frequency of fields applied, etc. So how does now from this atomic picture we go to sort of a macroscopic picture, right? So we have some bulk material and we apply some laser fields to it, and then some interaction occurs, and then the output we get some different fields, right? So on a macroscopic scale, how do we analyze the situation? So for that, basically what we do is derive what is called the nonlinear optical wave equation. Right? So basically what's happening is, so I have some medium here, right? Like a piece of glass or whatever nonlinear medium you want to look at, right? And it has atoms arranged within it, right? So if you zoom into an atom, it sort of looks like some nucleus with some electron cloud, right? And then we apply some external optical fields. which basically acts on this atom, induces some dipole, right? That's what we analyzed with the classical anharmonic oscillator model, right? So it induces some atomic dipoles. This is small p here. Again, so this is some atomic dipole, which could have a linear and non-linear component, right? And then if you look at the material as a whole, the atomic moment per, so I could denote this, for example, as mu. So the dipole moment per unit volume in the macroscopic medium is denoted by this capital P polarization, right? And that basically acts through the Maxwell's equation, right? So it acts through the wave equation basically as a source term. So we'll see how this term comes. Right, so basically this P acts as a source to generate more radiation or waves, right? And then basically this generated radiation now acts back together with my input fields and then acts back on the atoms, etc. Right? So this sort of cycle goes on in the steady state. Okay. So basically, the idea would be to start from the Maxwell's equation and get some kind of coupled equations, which sort of link the different fields that I apply here, and also the generated fields that I get out of the medium. Right? Basically, finally, we are interested in what optical fields we can generate, right? Depending on what kind of optical fields we can send into the medium. So yeah, keep this picture in mind. So we start with the Maxwell's equations in sort of dielectric medium, so no free charges, and also non-magnetic. Okay, so basically almost all of the materials that we use in nonlinear optics are dielectric and non-magnetic. So we consider only that case. Right, so the Maxwell equations are 4 of them, right? So I'll denote the fields with, so this tilde on the top denotes some rapidly varying quantity, right? So some oscillating quantity at the optical frequency. And then this, to denote the vector, I'll denote with a bar on the bottom. Okay, so this denotes vector, this denotes rapidly varying. Right, so simulate del dot B 0, and then the other two are the curl equations. Right, so non-magnetic material means basically mu is mu naught, so B is mu naught H. Okay, so if you recall how you derive the wave equation, like in a general non-linear case or in free space, for example, you start with these curl equations, right? And then take curl of one of them again, right? So for example, if I take the curl of this del cross E, on the right hand side I have right. So I use the vector rules here for curl, right? So you get del of del dot E minus del square E. So del square is del dot del, right? And here for del cross B, we put V naught del D by dt. So you get a double derivative in time now. And then also D, we know that I can write as epsilon naught E plus the polarization. Right. Okay, so now we make an approximation. We basically say that the del dot E is basically either identically zero or negligibly small, so that it can be neglected, right? So, for example, if you consider a plane wave, this is identically zero. Okay. For linear isotropic materials, it's also zero, right? Because so for isotropic materials, I can write D as an epsilon E, right? Where epsilon is now a scalar for isotropic materials, right? So from here, I directly get that dot E is zero, right? So this is identically zero for isotropic materials in the linear regime. It's also identically zero if I consider a plane wave. Right? If I consider an ideal plane wave, then del dot E is also zero. It's a transverse wave, right? Which does not depend on. So the electric field does not depend on position. So basically, what is del dot E in general? So from del dot D equal to zero, if I put D equal to epsilon naught E plus P, basically I get del dot E as minus 1 by epsilon naught del dot P, right? So basically, if the polarization in the medium has some sort of divergence to it, then this can be zero. In our case, as I said, mostly this term is extremely small, right? So the only contribution for this is either like from the nonlinear polarization, which we know is much smaller than the linear case, right? Because we treat the nonlinear terms as perturbations. Or if you have some complicated anisotropic materials, this could be non-zero. But again, the values are typically quite small. Okay. So basically, in most cases, we just neglect this, right? And it's a very good approximation. So basically get rid of this term. Okay. Yeah, so then if I get this first term of the double derivative of e to the other side, you see we end up with sort of the wave equation that you'll be familiar with, right? Del square e minus, so mu naught epsilon naught gives me 1 over c square. Right, so that's the wave equation for the electric field. On the right hand side, I have this term of the polarization which is remaining. Right, so you can see that, so this is a wave equation with the source term on the right, and the source term is basically the polarization, right? Or more explicitly, the double derivative or the acceleration of the dipole charge. Okay, so yeah, so let me start with, or go ahead from that point. So again, in most cases, we'll be looking at different monochromatic fields interacting with each other, right? So now we can write the electric field as a combination of frequencies. Right, so electric field is a function of both position and time. So I write it as I separate the spatial dependence and put the time dependence as just a harmonic term at a particular frequency. Right, and then you could have a bunch of different frequencies. Complex conjugate to make it real. Okay, and similarly, the polarization induced in the medium also I can write like this. So this is a vector now. Okay. So now if we plug in these forms for the electric field and polarization into the wave equation, right? So you can see that the double derivative d square by dt square will give me omega n square, right? So it will give me omega n square in the front for both the electric field and the polarization, right? And then again, if this equation has to be valid for all different frequencies at all different times, then we can just look at the individual coefficients of individual e to the I omega n t terms, right? For each omega n, and say those have to be equal. So you can see that from that we can get okay. So if you look at some component n at frequency omega n, I can write for that particular frequency the wave equation reduces to this. And now, so this is the total polarization. It includes both the linear and non-linear, right? So to explicitly see the effect of the non-linear polarization, we split this into a linear term plus a non-linear term. right? And the linear term we can just write as the linear susceptibility, right, at frequency omega, right? So this is, we're looking at frequency or omega n at frequency omega n. Times e, right? So that's the linear part, right? So that's also proportional to En. So we can take that term to the other side and combine with this term En on the other side, right? So then we get right, and then 1 plus chi we know is basically just the refractive index or square, right? Refractive index is the square root of 1 plus. So 1 plus chi is the permittivity, right? And this also at omega n, right? So basically we end up with this equation, which is some you might have seen before, like it's called the Helmholtz equation or something, del square plus k square of n of E, right? So for in free space, typically we put right hand side 0, or for linear materials we put right hand side 0. But here basically you can see that now the nonlinear polarization is acting as a source term, right? So it's driving the generation of fields. Okay, so yeah, so you can write this thing omega by c times n as k, right? So you can denote this as k n square. So
You're not able to.
sorry.
It's blank now. We are not able to see the blackboard.
Okay. Can you see now?
Yes, sir.
Okay. Yeah. So this is familiar del square plus k square of E, right? So now what happens to fields as, so for example, if you are propagating in a linear medium, we know that nothing happens, right? Basically the fields propagate. So let's say if you have some plane wave or something incident in a linear medium, basically it just propagates with velocity c over n through the medium, and the amplitude remains constant, nothing really happens, right? But in a nonlinear medium, so let's say this is some nonlinear medium. So let's call Z my propagation direction. Right, and then I have some, let's say, optical field with some transverse profile, like it could be simple plane wave with no profile, or it could be some, so this is my En of R, right? So it could be like a waveguide mode, for example, like an optical fiber mode or waveguide mode, or just a focus beam, or right, whatever. Right, and then so we send this beam through the nonlinear medium. And basically, through the nonlinear interaction, what happens is now the amplitude of the electric field actually starts depending on the z coordinate or the propagation, right? So if you have a linear medium, nothing happens, right? This amplitude, all you acquire is a phase, e to the ikz, but the amplitude or the intensity in the beam remains the same. Let's assume like there's no absorption. We are looking at again the case, let's say far from the band gap or something. So then all you acquire is a phase, and then the intensity or power in the beam remains constant. But we'll see that because of this nonlinear polarization, now fields can actually interact with each other and exchange energy, right? So the amplitude now will start depending on the propagation coordinate, right? So I can write this En of R as some An of Z, right? So that's my amplitude dependence that I want to solve for, and then I explicitly take the phase dependence already. So I take ANZ times e to the I k nz, right? So for example, in a linear medium, I know my solution ANZ will be constant. Okay. In addition, if you have a waveguide mode or some fiber mode, then in addition you will also have some transverse mode here, u of x, y. But that sort of we assume will remain unchanged, right? Because that is decided by your waveguide or fiber cross section or the refractive indices of the medium, right? So the only change that is occurring is sort of in the amplitude or the intensity as it propagates along with it. Okay, so basically then the next step is just to substitute En equal to this An of z times e to the I k n z into this equation. Okay. So here we've only taken the z dependence, right? So that means the del square, only the d square by dz square term will contribute, right? So let's look at what that will give us.
Hello, sir.
Yeah.
Sir, if we consider that the plane wave incident on the nonlinear medium, so there will be no change in the transverse mode of the electric field amplitude.
Yeah. So what? It could be a plane wave. It could also be some waveguide mode or fiber mode. So you could have some transverse cross section. But what we are saying is that as the fields are propagating, that transverse cross section is not changing. So the modes are remaining the same. Only their amplitude or the energy in those modes are being changed because of the nonlinear interaction, which is basically the case in most interactions.
Sir, it really happens
Sorry?
that the trans. Sir, it really happens in experiment that the transverse mode do not change.
Yeah. So what we are doing is like sort of like a modal analysis, right? So we are looking at, okay, how much energy is in this particular transverse component, right? So we are sort of we are doing a modal analysis in a certain set of transverse modes, and we are seeing how the energy changes in that. If you of course look at the whole thing as a composite, then of course maybe the composite mode that you get out might look slightly different depending on the interaction, because if you add up all the energies in the different modes, then the final thing, the intensity pattern that you get might be different, right? But here what we are saying is, we are saying, okay, let's split all the different modes and they are all interacting with each other, and what they are doing is changing the amplitudes in each of the modes, right? So the amplitudes and each of the modes will not be in general equal to the to those amplitudes at the output. So if you add all of them together, the final intensity pattern might be different at the input end. I don't know if that's clear.
Okay, sir.
But typically, like when we do some interaction, we also pick some particular transverse modes that we want to interact with each other. Okay, so we'll see in more detail how that works. Also, typically what happens is, especially in waveguides, different transverse modes have different propagation constants, right? So this Kn actually depends on the mode here, right? And we'll see later on that this Kn is actually very important. So that figures into something called phase matching. So for the nonlinear process to be efficient, we require something called phase or momentum matching, right? So only turns out that only certain transverse modes satisfy that, and most of the other modes don't satisfy that condition, so they don't interact at all. Okay, so basically del square of En, when we take En as An of z times e to the I kn of z, just becomes del square by del z square of An e to the I kn z. Right? Now An is also function of z.
The screen is blank again. I'm not able to see the blackboard.
Okay, I don't know why this keeps happening, but let me. Okay, hopefully it's back again.
Yes, sir.
Yeah. So yeah, basically you just apply the chain rule and do this by parts, first one derivative and then do the second derivative. So if you go through the whole thing, you will see that this gives you okay. So if you just do this, you get.
The screen is again black, sir.
I don't know why this happens. It's strange. Because from my side, it's still video is streaming. Okay. Yeah, right. So the first term here becomes this. The second term, this one is again just so this whole term is kn square times an e to the I kn z. Right? So you can see this term cancels out this term. Okay. And on the right hand side, let's keep this. So on the left hand side, now we are left with these two terms. Okay. Now we make another approximation. So maybe I'll just write this on the right hand side. So now we make another approximation which is widely used in optics, which is called the slowly varying envelope or amplitude approximation. So basically what we are saying is that we neglect this first term. So the double derivative of the amplitude, we say is much smaller compared to the second term. Okay, so you can see that. So if you look inside the medium, An let's say has some variation, right? So this An of z, right? So dA by dz gives me the slope, right? The rate of change of the amplitude. and the double derivative gives me how the slope is changing. Okay, and basically, if I say the double derivative, or maybe I write it like this. So the derivative of the slope is much smaller compared to this factor kn times the slope. So kn is basically 2 pi over lambda, right? So if I say I just have 1 over lambda here of the order 1 over lambda, right? So I'm saying this. So I'm saying that the rate of change of the slope is very small, such that, or is small enough such that over one wavelength, right? So let's say my wave is propagating like this. This is one wavelength. So the change in so this envelope or the amplitude, the change in that the amplitude, so the dA n over this over a wavelength of propagation is very small compared to the, let's say, the amplitude itself. Right, so the fractional change in the amplitude over one wavelength is very small, negligible. Right, so that's the slowly varying envelope of approximation, which works in, again, I would say 99% of the cases. Okay, only in certain very extreme cases where you can generate very large non-linearities, or you have very, very intense pulses, let's say of a few cycles or something. Only in some very extreme cases you have to take this term also. But in 99% of the cases, basically the amplitude is varying slow enough such that this is a good approximation. Okay, so that's what we do here, and so we just neglect the first term and just keep the second term. Okay, so now you can see it finally reduces to a very simple equation. So it's like just a linear differential equation for the amplitude. Okay. So you could have, like, let's say n different waves propagating in the medium. So you have n different equations, right? So the amplitude of each wave is now described by this simple linear differential equation, where again on the right hand side I have the nonlinear polarization. Okay. So this is called the canonical propagation equation of nonlinear optics. Basically, if you want to look at any nonlinear interaction in general, you start with this, right? So I can write down. So basically, there will be a bunch of coupled equations, right? So amplitude of each field, and for the particular interaction, I just plug in the nonlinear polarization term corresponding to that interaction, right? And then solve those coupled equations to see how the fields evolve. Okay, so this is called the canonical propagation equation, and I don't know, basically all of nonlinear optics can be analyzed starting from here. So that's a very important equation. So just a note that So let's say for plane waves or something, we don't have to worry about the transverse profile here, but like if you take some fiber or waveguide mode, like typically you have some mode profile here, right? Let's say u of xy in the transverse plane. So that u of xy solves the transverse wave equation, right? So I don't know if some of you have done courses in fiber optics or integrated optics, you'll know how to solve for modes, right? So this is some solution of the transverse part of the wave equation. And typically, sometimes for the mode, instead of k, we write beta as the propagation constant, right? So that beta is like k, except instead of the refractive index, we have something called the effective index, right? Which depends on, so let's say you have a fiber, for example, with a core and cladding refractive index, and my mode profile sort of extends out into the cladding a little bit, right? So then n effective lies between my core and cladding refractive indices. So basically, if I'm looking at some fiber or waveguide mode, the only change that happens is that you have to explicitly, so instead of the refractive index here, you get the n effective for that particular mode. Okay, and you have to keep this, if you're looking, let's say, at the interaction of fields in different modes, then you have to keep explicitly take the transverse also here. So like you take the transverse field here, and this P nonlinear will have a product of fields, right? Depending on which nonlinearity you're looking at, and each of these field terms you'll have to also take that corresponding transverse mode profile. Okay, so a little later in the course we'll go sort of we'll see how that pans out, and that gives rise to something called like overlap factors and effective mode areas, etc., which factor into your effective nonlinearity, right? So even for a given medium, so for a given material chi3, for example, we can engineer the modes and these profiles such that effectively we are boosting up the interaction strength, right? So for the same material, but just engineering this modes and cross sections, etc., we can get an effective nonlinearity which is stronger. Just to point that out, we'll later in the course. Right, so there are factors of u here also. So some u1 of x1, u2.
So video is again not visible.
Okay, so but yeah, just keep this canonical propagation equation in mind. So basically, it's just a first order differential equation for the amplitudes, and on the right hand side you have the nonlinear polarization, which drives the amplitude, right? And through this nonlinear polarization will be a product of the fields, right? So we'll get a bunch of coupled amplitude equations. So maybe let's look at a specific example to make it more clear. is this visible? I hope the ink is not too light, or is it visible? Or should I switch to a darker pen?
Now it is visible.
Yeah, but can you read the text easily, like, or do you want something darker? The ink, do you want it darker, or is it okay?
Now I think it's okay.
Okay. So yeah, just let me know if it becomes too light and you can't read or something. So I'll switch to a different pen. Yeah. So in any nonlinear interaction, basically we start from those canonical propagation equations and then get a set of what are known as coupled amplitude equations, which we then solve for to see how each field is propagating in the medium. Right. So consider a case, for example, let's say I have some chi3 medium here, and I'm sending 3 input waves at omega1, omega2, and omega3 with some amplitude A1, A2, A3. Right. So we know, for example, due to the chi3 interaction, I can get a frequency which is the sum of these. So omega4 equal to omega1 plus 2 plus 3, which is generated. Okay, so like at the output, in addition to these 3 fields, I could have another one which is omega4 with some amplitude A4. Right, and then inside the medium, all of these A1, A2, A3, A4 are a function of Z, the propagation direction. Right, so let's say my medium goes from Z equal to 0 to Z equal to L. Okay, and basically I have 4 inside the medium. I have 4 different fields present. So the electric field corresponding to any right. So I can write like this, where I could be 1, 2, 3, 4. Okay. Or maybe I should write this as n instead, since I was writing n. Right. So basically, I can write 4 equations, right? For so dA1 by dz equal to something, dA2 by dz equal to something, dA3 by dz equal to something, dA4 by dz equal to something. Okay, and so I get 4 equations which are coupled to each other. So again, the canonical propagation equation is this. Right? So I just plug in n equal to 1, 2, 3, 4 into this. Right? And for the P nonlinear, if I'm looking at this interaction, I know this is a chi3 interaction. Right? And I can write the third order polarization corresponding to this interaction. So, for example, if I put n equal to 4, I can write dA4 by dz, which is the wave at frequency omega 4. Times the third order polarization at frequency omega 4. Okay. So what is now this third order polarization at frequency omega 4? Right? So we know third order polarization we can write as so now I have again some degeneracy factor, so which will be 6 in this case if omega 1, 2, 3 are different, right? Then chi 3. So let's assume we are working in the Kleinman symmetry limit where chi 3 is some constant, right? It doesn't depend on frequency or anything. And this will be times E. So E1 at omega 1, E2 at omega 2, and E3 at omega 3. Right? I hope this is clear. So omega 4 is omega 1 plus 2 plus 3, so which I get by multiplying the corresponding electric fields, right? And so for E now we substitute, if we substitute, so here we've taken out the time dependence, right? So if you remember how this came from was we wrote P as some P of omega e to the minus I omega t, and E is also like that. And then we compared the e to the I omega t terms, right? So this was going as e to the I 4 omega t, omega 4 t, and this is e to the I omega 1 t, e to the I omega 2 t, e to the omega t3. When I multiply, I get omega 1 plus 2 plus 3, and then I compare the similar time variation on both sides. So then what is remaining here is basically the spatial part, right? So or here is just z, right? And this is also a function of z now. Right, so here I can put, so E1 is A1z times e to the I k1 z, A2 to the I k2, right? Because I've taken E as this. Right, so you can, so I'll get a term here which is yes.
The video goes away, sir.
Yeah. So I'll get a product of A1, A2, A3, and then I'll get e to the I k1 plus k2 plus k3. Right, so that will be my nonlinear polarization induced at the frequency omega 4, right? So it goes as e to the I k1 plus k2 plus k3 times. Okay. So the polarization of induced in the medium also, of course, varies with Z, and there is like periodicity and phase associated with the nonlinear polarization also. So basically, now we plug this in for the nonlinear polarization into the into the propagation equation here, plug P3. So you can see that, so of course I get the product of the three amplitudes A1, A2, A3. And then for the phase term, I get K1 plus K2 plus K3. And then I already had a minus K4 already in the equation, because An had a e to the minus Kn. Right? So I get some e to the I K1 plus K2 plus K3 minus K4. So basically, in the end I can write the equation for A4 . Okay, and I define this quantity delta K as K1 plus K2 plus K3 minus K4. Okay, so that's some sort of phase mismatch. Okay, you can see it's sort of the three fields which are adding up, we add those wave vectors, and the field which is getting produced, we subtract that wave vector, right? So it's sort of the total input wave vector minus the total output wave vector, right? It's some sort of wave vector mismatch there. Okay. Similarly, so let's look at the other term. So if I want to write an equation for A1, right? So I start from the general one. So I just put n equal to 1. And now I want to look at the third order polarization, which is induced at frequency omega 1. Right? So that will come in here, because that will drive the wave at frequency omega 1. So how will I write this? The nonlinear polarization induced at frequency omega 1. So on the right hand side, of course, I need to have some chi3, and then I need to have product of three fields, right? And the degeneracy factor, etc., is the same. Or, yeah. So what three terms will come here? So again, we are looking at something which varies as e to the I omega 1 t, right? So which electric fields components would we multiply such that finally we get something which goes as e to the I omega 1 t.
E3, E4 star.
E3, E4 star. Yeah, so I need three terms, right? So we can see from here, omega 4 is of course omega 1 plus omega 2 plus omega 3. So omega 1 I can write as omega 4 minus omega 2 minus omega 3, right? So basically what I'm saying is I can write e to the I omega 1 t as e to the I omega 4t times e to the minus I omega 2t times e to the minus I omega 3t. So you know the electric field is something plus complex conjugate. So this comes, if this comes from the, so e to the I omega 4t comes from the, I don't know, first part, A4, then the other two are minus sign, which means they come from the complex conjugate part. So they will have conjugates. So A2 conjugate, A3 conjugate, and then I'll have corresponding phases with them. So for A4, I have e to the I K4s. And for these two, I have a conjugate, so I have minus K2 minus K3 times Z. So is that clear? How I wrote that?
Yes, sir.
Okay. So now we plug in the third order nonlinear polarization at omega 1 into the equation for A1. So now you see, so adding on to this, I'll have another minus K1. So you can see basically what we'll end up with is K4 minus K2 minus K3 minus K1, which is minus delta, minus of this, right? So the equation for box this. So if I just plug this in here, the equation for A1 will be okay. And similarly for 2 and 3, you can just replace 1 by 2 and 3, and then so for 2 you get dA2 by dz. Here all these will become 2, and then here you get A4 A1 conjugate A3 conjugate. Right, similar fraction. Similar for 3, you get 1 and 2 here. Right, so you get 4 equations, and you can see all of them are coupled to each other because, like, for equation for A4 has A1 into A3 on the other side. For A1 it has A2. Right, so in general they are all coupled to each other. They are all nonlinear differential equations because on the right hand side you have nonlinear terms, right? So in general, it's in general, if you want to solve such equations, it's not trivial at all, right? And in many cases, there's actually no known analytical solutions. You have to like numerically solve them. But we can get some insights again in some approximate regimes of operation, right? So one such case is the undepleted pumps. Just draw the interaction here. Screen went
Replace
black.
again.
Sorry?
Screen is again not
Video goes
visible.
away, sir.
Okay, yeah. Do that again. Yeah, so you can look at what is called the undepleted regime. So usually, typically, the input waves or the strongest input waves. Sorry. Is the screen visible now?
So, yes, sir. Now it is visible.
Yeah. So I'm saying that let's solve this equation in a very simple case where we say that the input fields are very strong, right? And the conversion to A4, let's say, is weak enough such that we can approximate that the input fields are undepleted. Okay. So typically, the strong input fields are denoted as pumps in the nonlinear optics terminology, right? So this is called the undepleted pump regime. So we are saying that the input fields are very strong, and the conversion is small enough that we are saying basically the A1, A2, A3 remain undepleted. So we are saying A1Z is basically just A1 at 0. It's not getting depleted much. Similarly, A2, A3. Right, so we are saying basically A1, A2, A3 are not a function of Z anymore. Right, so they're just constants, which are sort of the input amplitudes. And it's actually, we'll see later that in nonlinear optics, actually it's very difficult to engineer cases where you get very strong conversion. Okay, so many times you're actually in this regime where the conversion is very small, let's say 1% or something, and 99% of the input power stays, or the input is not depleted much, right? Only if you engineer your nonlinear interaction extremely well, and then everything else is set up, you have enough power, etc. Losses are low enough. Then you can, in certain cases, get a large conversion, but it's actually quite difficult to do that. Okay, so basically what we can do is, so now it's just straightforward integration, right? All of this is just constant. The only Z dependence is in the exponential here. Right, so I can straightforward write my output amplitude A4 at frequency omega 4 as so the product of the input fields, and then I just integrate from this exponential factor from 0 to L. Right, so this integral gives me e to the I delta k L minus 1 by I delta k. Right. And now typically, like in an actual experiment or something, we'll measure the intensities of power, right? You don't directly measure fields. We measure the intensity of power. So if we want to look at the intensity, so the intensity in the generated field, of course, it's proportional to mod square of the amplitude, right? So again, this is at L. Right, so basically I take mod. So let's see, we get some constant factors here. You get mod A1 square, mod A2 square. So sort of the product of the input intensities. And then you get mod square of this. Right, so mod square of that, you can convince yourself is that where sync, as you know, sync of x is sine of x by x. Okay, so here I get sync squared. So okay, I get L squared. And sync squared of delta k L by 2. Okay, so this mod A1 square, mod A2 square. So mod A1 square is proportional to the intensity of field 1. Right? So I can write this as I1, I2, I3, again by including these factors. Finally, I can write I4 Okay, so I can write I4, the intensity of the generated wave at omega 4 as some constants, which, so you have refractive indices at all the 4 frequencies, you have chi3 square, and then you have a product of the input intensities I1, I2, I3, and then you have a square of the length, and then this factor of sync square delta k L by 2. Okay, so things to note: the output intensity depends on the product of the input intensities. So it's a nonlinear effect, right? You can directly see that. It depends on the intensities of the input waves in a nonlinear fashion. It's proportional to the square of the nonlinear element chi3, right? And it's also proportional to the square of the length. So what is it saying? Basically, if you look into the medium, what's happening is, so I start from here, right? And then in the first small section, I generate a small wave at omega 4. Okay. Then I propagate some more, and then I generate another small wave from the next section. Right. I keep generating these waves at omega 4, and basically the electric fields are all adding up constructively to finally give me a macroscopic field coming out of the medium. Okay, so since the fields are adding, right, so they add up along the propagation length. So the field goes as the length, and the intensity goes as length square. So this is showing you it's like a phase coherent effect, right? So typically, if you have an incoherent effect where you're just adding intensities or something, then it will scale as the length. But here you're seeing that it scales as the length square, which means it's a phase coherent effect, right? So fields are adding up. And then finally, you have this factor of sin square where the delta k comes into the picture. Okay. So if you plot this function, sin square, I'm sure, and if you must have seen it in some context or the other. So basically, if you plot sin square, it peaks at 0, right, and then it goes rapidly down, and this has some small side lobes. Right, so peaks at 0, then it has minima pi, 2 pi, etc. Right, so this is sin square x versus x. But at 0 it is 1. Similarly on the other side. Right? So the argument for sin square here is delta k L by 2. Right? So you can see that this factor is close to 1 if delta k L by 2 is close to 0. So if I am close to 0, then this factor is close to 1, and then I get this expression. But for example, if this becomes close to pi, then this factor is basically close to 0, and then I'm not getting any conversion at all. Right? So that's where this phase mismatch comes in, right? So right, so basically you want delta k to be sort of less than pi over L, right? So to be in this range. Such that for the conversion to be efficient, right? If your delta k exceeds those values, then if the conversion that you're getting is suppressed, right? And so basically what's happening is you go back to this field picture. So if you remember in the propagation equations on the right hand side in the driving term, there were these phase mismatch terms coming up, right? E to the I delta k z. So basically the waves being generated, or the small wavelets being generated in the medium, have phases associated with them, right, which depends on this delta k. Now if delta k is, let's say, 0, then all of these waves add up in phase and you get a big wave out, right? So that's when the conversion is efficient. But if delta k becomes large, then basically all these wavelets are out of phase and they destructively interfere to give you nothing at the end. Right? So to make, and this is true for, I mean, we looked at a particular type of nonlinear interaction, but you could take any type of nonlinear interaction in the undepleted regime. When the inputs are assumed to be undepleted, you will always get this sin square factor. Okay, because for any nonlinear interaction, you'll always get that e to the I delta k, but that delta k will of course depend on the type of process, but you'll get some delta k factor there, and it will show up finally as a sinc square in the output intensity. Okay, so this is true for any nonlinear process. So to make any nonlinear process efficient, you want to make that delta k as small as possible, close to 0, right? And certainly less than this if you want to make your process efficient. So pi over n, less than pi over n. Right. So if you look back at what delta k is, again, right. So delta k was k1 plus k2 plus k3 minus k4. So it's some wave vector mismatch, right? So I'm adding k1, k2, k3, and then seeing how it compares with k4, right, which is my generated wave vector, right? So if these add up to k4, then delta k is 0, and that's when I'm phase matched. So you know that the k, like in the quantum picture, I can write sort of the momentum of the photon as h cross k. Right. So you can also look at this as momentum conservation. Right. So k1 h cross k1 plus h cross k2 plus h cross k3. I erase the level diagram, but right. So in this picture, what's happening is I'm taking a photon at omega 1, omega 2, and omega 3. Right, and then annihilating these 3 photons and then converting it to a photon at omega 4. Now, if omega 4 is equal to omega 1 plus 2 plus 3, like from the level diagram, then energy conservation is automatically satisfied, right? H cross omega 1 plus h cross omega 2 plus h cross omega 3 is equal to h cross omega 4. So that's energy conservation. But we know for any physical process, in addition to energy conservation, you need momentum conservation, right? So the momentum conservation shows up like this in terms of the wave vector, because we know for photons basically the momentum is h cross k, right? So this is basically some sort of momentum mismatch, right? So one thing you can think about, so for example, when we have like balls colliding in mechanics, basic mechanics, we see these kind of problems, right? Some two balls coming and colliding and going away from each other. So typically we do energy conservation and then we do momentum conservation, right? And then we require that both of these are exactly satisfied, right? So the input energy is equal to the output energy, the input momentum is exactly equal to the output momentum. So here energy conservation is being satisfied exactly, but you can see here that delta k, of course at 0 you get the maximum conversion. But even away from 0, for non-zero values of delta k, which means momentum is not exactly conserved, you can actually get some conversion. So how is that happening? Physically, you can think about. So is it violating momentum conservation somehow? So I'll leave you to think about that a little bit more. The clue is sort of here, right? So there's a factor of L coming, right? So equivalently you can, so here there's a delta K times L coming to the picture. So that should remind you of something. Yeah, so maybe I'll stop here and take any questions. People have any questions?
So the basic question is, just now you just told us to think about if one of my any momentum is like minus k, means like going opposite to it. So the moment conservation of momentum is not followed. Why it is so, right? The question is.
No, I'm saying so. Like again, go back to that balls colliding, like in mechanics. So we write an equation for energy conservation, right? Some input kinetic energy is equal to output kinetic energy, And then we write a momentum conservation equation. Input momentum is equal to output momentum, but we write equal to, right? So in the mechanics case, we say delta P, where the momentum change is equal to 0, right? That, I mean, for the process to happen. But here we are saying that the process, of course, is most efficient at delta P equal to 0. But even for delta P not equal to 0, there is some, I mean, the process is happening but less efficiently. So how is the process happening at all? I mean, if I look at the mechanical analysis.
So its answer comes from quantum mechanics, the uncertainty principle.
Yeah, so it's related to quantum mechanics. Yes, you're right. Again, the clue was, so the L is what? L is the length of the size of the medium.
So delta X is equals to.
And you are getting a product of delta K and L. Right? So delta K is sort of the momentum or the uncertainty in momentum. And L, so basically, if you get a photon out here, so I have some detector here and I detect a photon at omega 4, I cannot say where it originated in the medium. Right? There's no way for me to tell, okay, this photon was born here. It could, yeah, it could have been born anywhere in the medium, and there's no way for me to tell. So basically, there's a position uncertainty which is L, right? So you can see that the tolerance here. So bigger my L, so the longer my medium, the bigger my medium. The smaller the tolerance on L, on delta K, right? So I can tolerate a smaller mismatch for a larger medium. But if I have a very small medium, very thin medium, for example, I can tolerate a larger mismatch because the momentum uncertainty intrinsically is high, right? If you define the position more precisely, my momentum uncertainty intrinsically increases just from the uncertainty relation. I mean, basically what you're saying is that here you're dealing with waves, like the wave nature is, right, for optical fields, the wave nature is what is important here. Whereas in balls colliding or something, the wave nature is not important, right? Like you can of course define a de Broglie wavelength, etc. But you can think of them as point masses. So for that kind of case, you need exact momentum conservation. But since here you're talking about delocalized waves, then momentum conservation or the equivalent of momentum conservation doesn't need to be exact here because there is inherent uncertainty in both position and momentum. But yeah, so this is very characteristic of any nonlinear process. These things were kind of dependent. So basically, like, let's say you want to engineer some kind of nonlinear interaction for some kind of application, a major focus will be how to make this delta K close to 0. Okay, so that's where most of the engineering and your design comes into the picture. Because, so you can see here, so how are they related to the frequencies and refractive index? So K1 is just omega 1 by C times n at omega 1, right? This is omega 2. Right? So if now you know omega 4 is basically omega 1 plus omega 2 plus omega 3, right? So you can put that in here, and you can basically see that. So if all the refractive indices were equal, then this is 0, right? So if n at omega 1 was equal to n at omega 2 equal to n at omega 4, then this you can take that out common, and then you just get omega 1 plus omega 2 plus omega 3 minus omega 4, which is 0. Right? So if the only, or a priori, the only way you can get delta k 0 is if your refractive index as a function of frequency is flat. Right? So at omega 1, omega 2, omega 3, omega 4, it's all the same value. But of course, any medium you take, any material you take has dispersion, right? Which means like if you actually look for any real material n as a function of omega, it actually goes something like this, right? Typically, it increases with frequency. So of course, if I take some omega 1, omega 2, omega 3 values here and omega 4, you'll see the corresponding values of the refractive indices are such that this will be non-zero, of course, right? And typically, if you just take sort of the refractive index or the bare dispersion of the material, this will be typically too large, right? So it will be somewhere like here, out in the wings here. So basically, your conversion is, so basically what I'm saying is, if you take, let's say, 3 waves and you shoot it into a material, unless you do some design of the material somehow, it's very rare chance that you would see some output at omega 4, because this delta k is some large value and it's phase mismatched, right? So most of the, or a lot of the research in nonlinear optics is for some particular process. You're interested in some particular process that you want to happen with efficiency in some medium, and then how do you engineer the properties of the medium such that you can get delta k to be close to 0. Okay, so those are called phase matching techniques, and there are different kinds of phase matching techniques that people use for different kinds of processes. Like for example, in fibers or waveguides, one thing you could use is, so of course this kind of curve you'll get, let's say, for one particular type of mode in the fiber or waveguide, right? But if you look at some other mode, then you'll have some other curve, right? So maybe like if I choose different modes for these different waves, right? So mode 1, mode 2, mode 3. So for omega 1, I choose mode 1. For omega 2, I choose some other mode, omega 3, right? I choose different modes such that the refractive index variation with frequency is different. Then maybe somehow, so that's called intermodal phase matching. So that's one way, for example, to do it, right? There's birefringent phase matching, which some people write about. So that's more useful in Chi2 second order nonlinear cases, because most of the second order nonlinear materials are also birefringent, which means different axes, so different polarizations see different refractive indices. So for example, if you have these different waves of different polarizations, then again you have sort of different curves and you can phase match, right? Then there is quasi phase matching, which is also mostly used for Chi2. We'll see for Chi3 you can actually use the dispersion of the material itself for certain processes, like 4-wave mixing, which is an important process we'll see later on. You can actually use the dispersion of the material itself to your advantage, right? And we'll see how you can. So yeah, so there are different ways of dispersion engineering, basically, to satisfy the phase matching.